Welcome to this micro ED workshop. My name is Nei Xin. I'm a life science application engineer. Today I'd like to share with you how we can, using our Titan Krios microscope together with the EPU-D software, how we solve the structure of the small crystals and some of the drugs using the micro ED workflow. Alright, so let's move here. Here I'd like to share with you our EPU-D software. So let's start. So this software is an automatic data acquisition tool for the micro ED dataset. Yeah, if you have some experience previously with the EPU or Tomo, you can recognize the outline of the software is quite simple and similar to the other thermofisher software as well. Here we have different, move it a little bit to this side. Here we have a list of presets we can save our optical settings. Here we have Atlas, grid square, search, image acquisition, and the diffraction acquisition. So all these presets contain different optical settings and camera settings, which can help us locate our crystals, locate our region of interest, and acquire the diffraction image from that. So in the following, I can show you them one by one. And in this test, I have loaded the small drug target we call the eptofen. It's already loaded into the microscope. So first, let me open the column wall. Then we can acquire one Atlas image as a preview. Yeah, here we have some Atlas image. It's just an overview of the entire grid. You can see some grid squares with some dense particles. So this particle is just manually grinding the drug into smaller powder and apply to the grid. But before you load the sample, you need to using some nitrogen gas to blow away all the particles not strongly attached to the grid, but leaving only the one attached to the grid tightly. Then you leave it over there. So now I can move the stage to some of the small spot over here, which our potential target. I can move to the second, we call the grid square preset. So in this preset, you are going to acquire some images only within one single grid square, which can more precisely target your region of interest. Yeah, here you can see that we have a quantifoil carbon here. You can see some of the holes, and on this carbon film, you can see small particles. Some of the particles may be some like smaller ice chunks, for example, like this one, which is a hexagonal in shape. You can easily recognize them. And some of the particles is likely to be the drug crystals. So we can target one of them, that we can take a closer look. Maybe this one. So the next preset we call it the search preset. In this preset, it can give you a more closer look of your target. Yeah, now you can see this is our holy carbon, and within here is some crystals, could be our potential target. This red cross over here represents the position of the stage. Now you can see I move it, simply move it to the center of the crystal, and I can move to the next preset called image acquisition. And this is a preset that we can use to locate our region of interest and set our optics. And in the next preset, the diffraction pattern will be shared the same optic setting with your image acquisition setting. Yeah, that's good. You can see something in the middle of the beam. We can move slightly to the center, almost it here. Yeah. Then we can change to the diffraction acquisition. So this is something specifically special for the EPU-D software, which means we can acquire diffraction images directly using the software. And this software, when I click preview, They also give you a confirmation that do you really want to change your instrument projection to diffraction mode. Here I like to ask you pay attention because the diffraction mode will give you a very bright spot in the center. And in this case, you need a beam stopper to protect your camera. And in this workflow, we are using the theta camera, which is quite robust against high dose of reading. And we also have a very special camera set we call the theta D, which is specifically designed for the EPU-D for diffraction mode data acquisition. And now they give you the confirmation. If you click yes, the system will try to insert the beam stopper in the center. We already finished alignment, so the beam stopper and your diffraction spot will be aligned properly in the center of the screen. Yeah, here you can see that after inserting the beam stopper, we can block the really strong diffraction pattern in the center, and you can see all the diffraction patterns about this. And this software also gives you this resolution range. We can help you estimate what resolution you can achieve from these diffraction spots. By changing the different camera lens, we can change your diffraction patterns, make it spread wider. You see more information from the low resolution part, or can shrink it to the center, but you can see something more from the high resolution part as well. So from this, this drug target is likely to be currently we have the highest resolution about 0.8 angstrom, which is less than 1, which is pretty good from our reconstruction level. But from this diffraction pattern, it looks like more like to be ice cubic instead of drug target. Already can tell from the diffraction pattern, but it's okay. It's work for demo purpose as well. Okay, so now let's move to the EPU-D session. This is our data acquisition session. We can start a new session. Okay. We'll give a name of the session or change the folder of this session. Make a new folder. Alright. So this is quite important. It's automated data acquisition for your data set. In this acquisition settings, we can using the software to help us calculate your centric height. We can define your starting angle, your end angle, and the increment. So normally for the data set, it really depends on the tolerance of the target. For your protein crystals, which cannot take too much dose, which is very dose sensitive, we can set a smaller range of the starting angle and the end angle. Covering 20 to 20 is a good starting point. But for the drug target or some other small chemicals which can take slightly higher drug dose rate, we can make it to some higher angles, like minus 30 to 30. And also we can play around with increment. But here I like to leave it to 1 as a good starting point. So now I have set it the starting angle is minus 30 degrees and end angle is plus 30 degrees, so which means it covers 60 degrees in total of this crystal. And every 1 degree increment, I will take 1 images, which means I will going to have 61 images from minus 30 to plus 30. Okay, so before we start, we can using this auto-eccentric tool to help us to calculate the eccentric position of our crystal. By applying the auto-eccentric function, the software will tilt the stage from lower angle to higher angle and compare the images at different tilting angle. And based on the number of pixels shift, they can help you calculate what is your eccentric height. Now from the information panel, you can see the starting from 5 degree and up to 15 degree and now to 30 degree to further verify your Z height. Yes, around 30 seconds, you'll finish the autocentric. Yeah, but before we proceed, we can check again by checking our image acquisition to see if our crystal is still in the center of the image. Alright, here it is. Okay, so we finish our eccentric positions. We set up our tilting range, our increment, and the next is just give a name of this setup. Let's first over. Then we can start. And before you start your system, you're going to change from TEM mode to the diffraction mode. And this they give you a confirmation again. Then we can notify that you're going to change to diffraction pattern. Make sure you have your right camera, you see that camera, and the software will also insert the beam stopper. Okay, so now the state will tilt to minus 30 degree and starts the data acquisition from minus 60 degree. So every 1 degree tilt, every second, it will take 1 images. Now you can see from there, your stage is tilting continuously, and in the same time, you are going to collect a diffraction pattern at every 1 degree angle. Now we can play around the brightness, contrast, and the gamma of the image, but it is only for the display purpose. And the real image has its auto brightness contrast adjusted in the RNC format. You can see here your diffraction pattern goes all the way to 0.8, somewhere here. Yeah. Okay, after 60 seconds, we have collected our first micro ED dataset from minus 30 to plus 30 degree. And on the bar over here, you can see around 61 frames has been collected. You can drag around, you can see all the images, all different diffraction patterns at different angle. Yeah, if you're at a certain angle, if you're rotated properly, you can see that your unit cell is aligned very properly with the different pattern. You can see a lot of more repetitive patterns information. And just from this diffraction pattern, I can tell already there is two eyes cubic eyes like overlapping each other. Now you can see the pattern is you can see two crystals overlapping, then it's a hexagonal eyes. But the purpose for that is just to show you how this EPU-D works. Alright, yes. So next we can go back to our grid square. We can select our second target as well.